All right, welcome back everyone. So in this video, we are going to briefly talk about 6.2, line integral, which is our last concept in Calculus 3. Just be aware that, final exam will entire chapter 1, 2, 3, 4, 5, and just last unit in 6.2 in chapter 6. So this is not really, the final will not really focus on, this concept, but I just want to share with you because there are a lot of commonality between Calculus 2 and Calculus 3. So this is one of that concepts. So if I go down slowly, I just want to give you guys a little bit of a idea. In Calculus 2, how did you find out the area? If I'm giving you the function f of x, and then let's say we have a specific, interval on the x-axis from a to b. So in Calculus 2, by using that integral symbol, you were able to find out the area under the function from a to b. So now we have a similar idea. Now let's say we have a three-dimensional space. So let's say I have, three-dimensional. So we have a three axis. So let's say this is x, y, z. And, let's say we have, the function on the x-axis with respect to t variable. So let's say, we have one of the equation on the x-axis. Let's say that is a look like here. And then I have another line. And then that is also function on the y-axis. And then it is also with respect to t variable. So let's say I have those two functions. And then we have let's say we have a function z that is passing through only the z, coordinate points. So let's say, I don't know, I'm just trying to draw passing through this line like this. And then we have a z equal to some like a constant. So if I'm looking for the line, let's say we have t, so t must be between, let's say, a to b. So let's say I have, g of t, so on the x-axis. So let's say we have the line. So I'm going to get rid of this. So let's say I have g of a here. So that is aligned with the x-axis. And I have another line that is passing through the y-axis. So let's say we have h of b here. And then in this time, they're not the straight line. I'm just creating the situation. So something like this. Something, we have this line. So this is corresponding here, h of b. And then there's a corresponding g of a. So we have this. So if you see, it's a little bit abstract, but you see that? Like there's a, plane between a and b with respect to t variable. And let's say I want to find out this area in three-dimensional space. So this is a two-dimensional space. Let's say this is a three-dimensional space. So it's a little bit tricky, right? And then you feel like the idea is, oh yeah, I might be using the integral concept. So the idea is, what if your a is going to be from here to there? Yeah. So you have to cover like entire like volume under that shape. So this is a three-dimensional space. So we're going to do the same thing. We're going to use the Riemann sum. Do you remember that? Here, there is no particular formula to find out this shape. This is not rectangular. This is not a square. This is not a circle. So you cannot simply, length times, width is not going to give you that answer. So the idea was, if you remember, we have many infinite number of the rectangular. And then if you're adding all the summation of the rectangular, we were able to find out this entire area under the curve. So basically we are doing the same thing in three-dimensional space. you have many layers, right? You have many layers in this shape infinitely. And if you're adding each area of that shape, and then if your summation, ooh, we might be able to find out the entire, the area under the shape, according to this function, right? So that's a very corresponding idea. So mathematically, if I remember, we've been using the Riemann sum limit. We have infinite number of the, rectangular, and there's the function given. And then, we have a equal size of the partition, And then I forgot the summation here. So this is the summation, and equal to, 0 to infinity. So this is all the summation of the rectangular. And then you have infinite number of the rectangular. So later we talk about this has been improved in the general form of the integral. So basically we are doing the similar thing in three-dimensional space. You just have a couple, idea. So we have to use the same integral, okay? And then you have a limit. So I'm gonna use the limit integral. So in this time, we are dealing with either two variable or three variable, because this is a three-dimensional space. So let's say I'm gonna just beginning with the two variable of the function. And then in this time, right, you're gonna find out the area of each surface of the shape. So ds is a surface. So this is actually from the Riemann sum, right? Limit, the x infinity to the x, whatever the partition of x is going to infinity, and then summation I equal to 1, n. And then actually this one is n here, my bad. And then we had x, y, and then you're gonna find out the partition, all the equal lengths. So you're gonna find out the equal length of the, of the surface. And then same idea, you're gonna find out the area of each surface, summation, and then you're gonna take the limit. So we are going to do the similar work 6.2. And then the formula later in this time will be developed too. I'm going to show you, but just remember, this is very corresponding idea. But sometimes, if you have x and y variable, they have a different variable. For example, if you are just using the x and y equation, taking integral will be really complicated. So what I'm saying is, in this time, your function with two variable will be converted to the t with respect to t variable, so that you're going to take the integral with respect to t only, so that the calculation part will be much easier. So this will be changed to x over t. You're going to convert it x equation in terms of the t variable. That's actually we call parametric equation, if you remember, long time ago in chapter 1. So something, this is happening. And then I'm going to go down. I will show you entire equation. So this equation will be developed over the year. So this is the idea, actually, I explain it. Your f of x comma y, the two variable of the function, it's better converted to the parametric equation with respect to t. So that's something happening. And then you're going to have some order between a and b to find out the equal partition. So that's the s. So actually, I want to show you this formula. That's actually we're going to use it. So same thing, we are looking for the area, in three-dimensional space. So that's usually integral fx comma y dx or ds, doesn't matter. And then take the limit. This is a Riemann sum, right? You're going to adding all each surface of the shape, adding all of them, and take the limit. Later, this idea developed to this way. Make sure there are two different ways. Okay, one is, okay, This is the we call a vector line integral. So so this is the same idea. You converted whatever the f of x comma y into the parametric equation because t variable is easier because you're dealing with only one variable. And then you're gonna take the derivative of each x and y equation with respect to t and square, and then take the integral with respect to dt. So this equation, actually I show you, this is modified too. So same thing, more concretely, this is the equation to find out the area of the three-dimensional space. And then there are two different formula. One is using the parametric equation. Second, you might be using the polar coordinate system. So I will show you two different methods. So I'm going to highlight it different color. So we're going to utilize this formula to find out the area, like three-dimensional space area. Okay, so this is what we call line integral because we are taking the integral kind of like a line. It could be quadratic line, it could be any type polynomial line. We don't know what kind of line you're going to deal with, but we are taking the integral to find out the summation to find out the area in three-dimensional space. So if you think about this two corresponding, it's better to understand, but the main idea is you're looking for this image, kinda. So if you look at 6.2, honestly, there are so many words going on, but I just want to share with you, there are many commonality between 2D and 3D. Just formula slightly edit up, it's been edited. So that, take a look at it. I will use those two formula to find out the line integral in three-dimensional space. Okay, so let's take a look at one example. I'm not going to really focus on this topic because we had already we talked about so many different ideas, but this is one of them where you can find out the commonality between calculus 2 and calculus 3. So I thought that it might be helpful. So let's take a look at one example. So actually here. So let's evaluate the line integral. So that means they're gonna think about all the summation of the three-dimensional space according to based on this given function x, y. We have a two variable of the function, and then they're going to passing through this two coordinate points. So, okay, a lot of information is already given. So step one, we're going to do step by step. So this is the joining. So there is a line that is a joining negative 1,1 and 2,3 in the space, but we are not sure whether this is the straight line or curvy line. We don't know. So the best way to find out the direction of those two lines, we're going to calculate the vector. So we're going to find the vector between negative 1,1 and 2,3. So that it's going to be much clearer, what kind of, line we are dealing with. So vector, the AB vector that is passing through those 2 points. So if you remember, we are simply adding them. Do you remember how to find out the vector? So this is a direction vector specifically. So we are adding negative 1 plus 2, 1 plus 3. Actually, I made a big mistake. Why am I adding? I have to subtract, right? Because I'm looking for the, the length between 2 points. So if I recalculate it, sorry. So 2 minus 1, 3 minus 1. So the vector between those 2 points will be 3, 2. So first to define the direction vector between those two coordinate points, and then x, y, having two different variables, it's going to be complicated. So if you remember, I'm going to convert this one to parametric equation so that when you are taking the integral, taking the integral with respect to t only, it's going to be much simpler. So therefore, we're going to find out the parametric equation. So if you remember, to find out the parametric equation, you have x equal to something, y equal to something. And then the first one, you can choose one of the coordinate points. So I'm going to choose -1 and 1. So x is a -1, y is 1. And then you are going to use the following vector. So this is a changeable. So this vector, so if I have -1, 2, 3, this can be expanded, this can be shrink. We don't know. So that's why we have a plus 3x, but in this time 3t, and then plus 2t. So that's the role of the vector. It could be stretch, it could be shrink, depending on the scalar. So that according to the parametric equation, your x is going to be -1 plus 3t, and y is going to be 1 plus 2t. Depending on the t, this vector could be larger or smaller. Depending on the t, you can make this one, stretch or shrink. That's why this is the vector times t, vector times t. And then you're adding the given point because we are starting from here. If you want, you can use a 2, 3, it doesn't matter, okay? So that's a parametric equation with respect to t. So x is with respect to t, y is changing with respect to t. That's what we got. So now it's getting better. So we have all the information now, okay? So we are looking for the area x, y, ds. And then we are going to find out x is now -1 plus 3t, right? -1 plus 3t, y is 1 plus 2t. And then that's your parametric equation. And then go up, you're going to evaluate this part. The radical, you're going to take the derivative, so dx over dt. So if I have this information, you can find out the dx over dt, it is going to be 3. dy over dt, that is going to be 2. So here, 3 square plus 2 square, simply. And then you have a dt. That's it. Okay. And then one thing you could think about it, do I have the t variable? So let me think about it. We do not have a t variable, so the t variable should be given. So in the question, I might be missing. So t is going to be between 0 and 1. So we have changes between 0 and 1. So that this is a dt, we're going to plug in 0 and 1 simply. So the interval for t will be given. Okay, so that the x is going to be changing with respect to t between 0 and 1. Y is also changing depending on the t between 0 and 1. That's what they mean, right? All right, so now the rest of work is to simply take the integral. So we have all the information. 0, 1, you can use the distributive property, so the rainbow thing. Uh, 9 plus 4, what is that? 9 plus 4, 13 dt. So now I'm going to take the derivative because the radical 13 is a constant. And then I have -1. Nothing, we can combine it. So, oh, we can combine this two number. So that's going to be plus t plus 60 dt. And then take the just integral. So what is it? -t plus t second over 2 third over 3 from 0, 1. So radical 13 plugging 1, -1, 1 over 2. This is a 2 to the third. And then you're going to subtract 0, that is a 0. So at the end, you should get this one positive 1 over 2. 16, 2 times 2 times 2, that is a 16. So let me, oh, I made a mistake here. Why should I have 2 here? This is a 1 to the third. We have a 1, my bad. So it's going to be 2. So radical 13, what is it? 5 over 2 to the 4, 5 over 2. Did I calculate correctly? So I have 2 plus negative 1. So that's negative t. So I have 2 plus 1 over 2 minus 1. So if you calculate those number, negative 1 plus 2 is 1. 1 plus 2. So I have a little bit of typo. So let me just recalculate it. So we have a negative 1 plus 1 over 2 plus 2. Am I correct? So radical 2, this is 1 plus 1 over 2. So the answer is this. This is the area we are looking for between that point in three-dimensional space. Does it make sense? So that's something you can think about it in three-dimensional space. So we have a lot of formula, honestly, in Calculus 3. So the best way you can prepare for the final, organize each formula in each chapter. We have 5 chapters, so there are a couple formulas you can organize it, so you don't need to back and forth while you are taking the final. So that this is one of them. Okay, so I try to give you guys the idea. There are a lot of commonality between Calculus 2 and 3 concept. Just we are expanding the variable from 2 to 3 dimension, an extra variable. So that's one idea you can think about it. So likewise, I'm going to do one more example, almost done. So what happened is, so this is the case where you are using the parametric equation. Because we are, whatever the x and y equation is with respect to t variable. Second, method, you're going to use the R, kind of like a coordinate system. So let me show you that example. So this, no matter what you do, you're going to get the same answer. But depending on the given function, sometimes the second method might be helpful, or first, depending on the function. So let's take a look at that example. I'm going to go down here. So I try to, find out the image that I draw at the beginning in another textbook. So you can think about it. We are looking for the area, by adding infinite number of the surfaces. So let's say you have this question, and here is the function with 2x and y variable. So this is definitely 2-dimension. It's not 2-dimension, it's a 3-dimension, because we never know. It's a, there is a 3-dimensional space as long as you have 2 variable. So let's take a look at this. What is going on here? What is going on? So in this question, we have to take the integral 2y x second minus 4x, and they say that integral is a lower half of the circle centered at the origin of the radius 3 with clockwise rotation. So in this time, to represent the integral for x and y, they're giving you the radius. So the integral is related to the radius somehow. So if I just draw the image, lower half circle. So we have -3, 3. So, so in the 3-dimensional space, somehow you have a circle, and then there is a function. So these two ideas is going together. And then it's hard to imagine, but if you think about it, I don't know, we can think about, so there's a function going something like that. And then the radius is from -3 to +3. So if they're going down somehow, so the circle, they're looking for the half circle. Something like that. They're looking for that area, okay? So -3 to +3. So this is how we're gonna do it. We're gonna utilize, go up, this function, because R represents the radius. So maybe there's something we could try. So step 1 is we're gonna use, okay, polar coordinate system, and parametric equation both. Okay, so just so you know, the parameterization for the curve, if you remember, we have RT, yeah, and then R times cosine T, this is represent X, R times sine T, actually one is a negative, positive, this is to represent the Y. So this is the parameterization for the curve in terms of the T variable. And then this is the half. The T is going to be between 0 to pi. So this is something is a given you can think about long time ago. So in terms of the radius, you can represent the X and Y. R times the cosine T, that is the X equation, negative R times the sine T, that is a Y equation. So what that means is, we can say X equal to R is a 3 cosine T, Y equal to negative 3 sine T. So we have all the information now. This is something you need to catch up. And then according to the formula, let me write it. I'm going to write this. So the area, let me see that information. One of the equation is RT, absolute value, R prime T, dt. So we're going to use the second equation. So therefore, we have F RT. What is RT? We have 3 cosine T. And what we have? Comma, negative. So now this one should be just R, negative 3 sine T. So this is representing the function, right? Or if you're confused, I'm gonna step by step work for you. So we know this is X and Y. So we're mentioning this is what we're doing. So 2yx second or x ds. So we have to convert everything. So F RT and then R prime T dt. So here, what happened? We know we're going to convert xy in terms of the R, in terms of the T variable. So x 2 times negative 3 sine T, x 3 cosine T second power, minus 4 times x 3 cosine T. Am I okay?
Professor
So
Ben,
yes.
can I stop you a little bit?
Yeah.
Yeah, so I think as what I remember, the equation for the x equal r cosine t and y equal r sine t, no negative, right?
Yeah, but the reason why I have a negative because it's a half circle. So yeah, actually the formula it is positive, but the reason why I have negative because this is the lower half circle. So when you look at the radius, one should be positive and negative. So yeah, that's why actually you're right. This is a positive. If you go back to thank you for checking that formula. So it's a positive, but the reason why I have a y because one of them should be positive. One of them should be positive and negative because we have a lower half of the circle center at origin of radius 3. That means one is a positive 3, another one is a negative 3. So it's a little bit tricky. Honestly, I understand. So yeah, you're right. The formula is a positive, but the reason why I have negative is I just want to focus on one is positive and negative. So
thank you very much.
So let me just highlight that. Yeah. So far good, right? So where am I? So I'm trying to convert this one in terms of the T variable because this XY is bugging me. So this is entire thing we can convert, right? And then what are you going to do next? Just a little bit of breathe. You need to take the derivative, right? Derivative of the R equation. So if you're gonna do that one, what happened? I'm going to take the derivative, okay? And then just remember, many people forgot what that mean of the symbol. Do you remember? This is magnitude. That means magnitude. So whatever the component, you have a second, b second. So we're gonna do that work. So this is going to be radical. What is a? Which means our x second plus y second. So let me change x and y. So x is a 3 cosine t. You're gonna take the derivative, and then you're gonna take the second power. That's what the step. And then you're gonna take the derivative first and take the second power. So that's what this part, magnitude. Take the derivative and take the second power. So I'm sorry, this is a little bit of long, but you can have. So now I'm gonna just expand everything. So 2 times negative 3 times. So that is going to be negative 6 sine t. And 9 cosine second t minus 12 cosine t. So this is this part. And then the second part, anybody remember what is a derivative? Sine, the cosine t. Negative, this is gonna be negative sine t, so negative 3 sine t to the second. And then sine t, when you take the derivative, it is gonna be positive cosine. So I'm gonna keep negative 3 cosine t second power. All right, I'm doing, so far so good. So there's a dt.
Professor,
Yeah, what?
please
ahead.
add a derivative sign for the negative 3 sine t.
Yeah, so I took the derivative of the cosine t, that's a negative sine t.
Yeah, I
So-
just like to, do you add a derivative sign? The right, the sign up there, because I don't want to be confused while I'm reviewing.
Okay, so here, if you think about it,
Just add the sign like the first 3 cosine t. That's
you
it.
mean t here?
Yeah, yeah. There's a derivative sign there, right? Up of the t, right?
I see what you're saying. I see now. So
Yeah.
they're derivative. Yes, you're right. So this is derivative. Yes.
Yeah, I just need that. Yeah.
So
Thank
we
you.
took the derivative, right? Everything, dt, you took the derivative. And then I'm taking the second part. Yes. Okay. So if I remember, we have RT. What was it? 3 cosine t, negative 3 sine t, R prime, that is negative 3 sine t, negative 3 cosine t, and I'm taking second power, right? So this is going to be 9 sine second t, 9 cosine second t. Am I correct? So that's what is happening. Thank you. So for better your understanding. So now, keep going. Negative 6 times 9, negative 54 sine t, cosine second t. Ooh, negative 12 cosine t. And then we know this is 9 sine second t plus 9 cosine second t dt. Keep going. I cannot simplify anything, so I'm going to just keep negative 54 sine t, cosine second t, negative 12 cosine t. And then you guys know 9 common factor, and then sine second t plus cosine second t. Ooh, that is what, according to the geometric identity? Uno, right? This is going to be 1. So therefore, we have to just keep this, copy, paste, and then this is 9 times 1. So this is going to be just a 3 and dt. So we got it. Now just take the derivative, take the integral with respect to sine t, cosine second, and da 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 da. So the answer will be, I'm gonna bring 3, and I'm gonna we do have negative 54 sine t cosine second t minus 12 cosine t. You're gonna take the dt derivative. So what are you guys gonna do? How are we gonna take the integral? What kind of idea we could do? We can separate it. Minus 54 sine t cosine second t minus 12 cosine t dt. Yep. So I can bring negative 54 to the front. So 3, negative 54 sine t cosine second t dt minus 12 cosine t dt. See? And then we know the t interval, actually I didn't write it. Oh, actually here, 0 to pi. So 0 to pi. So we are taking the integral with respect to t. So that's something we're gonna deal with. Sine t times a cosine second. Okay, we're gonna take the derivative. What are you guys gonna get? What can we do? How can you take the derivative here? Anybody has an idea? Can we use a u substitution? What can we do? I'm not sure. Let's say u equal to sine t, du over dt. What is the derivative of the sine? It's a cosine, right? So it is going to be cosine. So du equal to cosine t times dt. So something we can combining. So now sine 0 is a 0. Sine pi is also 0. Oh, that's interesting. Sine pi is a 0. Am I correct? Because if you have in the sine function, sine 0 is a 0. Sine pi is also 0. Oh, this is a 0 to 0. Okay, that's getting interesting. So we have a sine t is a u. And then cosine t dt, this is going to be du. So u cosine t, that is going to be du, but it is going to be from 0 to 0. There is no area. So this part, I found out the 0 anyway, isn't it? So if I rewrite it, we need to do only this part. So take the integral cosine t. Cosine will be negative sine t from 0 to pi. So negative 12, negative sine pi minus sine 0. So what happened here? We have negative 12. Negative sine pi is also 0 plus 0. Oh, this is a 0 as well. Is there any mistake do I have? 1 second. We have negative 54 sine t cosine second t minus 12 cosine t, and I do have a 3 dt. So let me double check what is going on here. I took the derivative when I use a u substitution, but let me see if I can do something. So in this time, I see that it's a 0 for cosine t as well. So let's see, cosine t when I take the integral, it's gonna be negative sine t. Do you notice something? Is there any mistake?
I got the answer as 0 for second one, but first one in my calculator equals negative 36.
Can you repeat one more time?
The first one not equal to 0. First one in my calculator equal to negative 36. Second
How?
one is second one is 0.
Oh, how did you get 36 here? Where's my mistake?
Make cosine t as u.
Oh, so you said that cosine t is u. Okay. So let me try it that way, because this is we keep getting 0. So let me try to change u substitution instead of sine. So let's say u equal to cosine t du over dt. So that is going to be negative sine t, right? So du negative sine t dt. Okay, so now we have 0 to pi, not the 0 to pi. So u 0 cosine 0 is 1. U pi cosine pi. So if I have 0. So we do have 0 to 1. That's better. And then sine, still there. Actually, sine t times dt.
Cosine pi is -1.
Negative 1, thank you. So negative 1. So sine t, so let me write it, sine t here. So cosine t is a u square. Yeah, that's going to be better. U second power. And then we do have negative du. Yep, because the sine t times the dt is negative du. I like this way. So u to the third, 3, negative, from negative 1. Thank you. So this is a better. So if you take the subtraction, what are you guys gonna get? Negative 1 over 3 minus negative 1 over 3. Am I correct? So negative 1 over 3, positive negative 1 over 3. I have negative 2 over 3. Am I correct? Are you guys okay? Yuen, did you get the same answer with me?
You forgot negative 54.
Yeah, and then we're gonna keep going. So here 3, so let me change the color. We had a 3, negative 54. So we got this part, negative 2 over 3, good. And then we got this part 0 anyway, good. So therefore, double negative change to positive. And then 54 divided by 3, yeah, we can do that. What is it? 18 times 2, I got 36. So therefore, it is going to be 108.
But I got negative 36.
Negative,
And in my side is 2 over 3, not negative 2 over 3.
is there, so let me double check. So we have, this is f of 1, f of negative 1. So this is negative 1 to the third. So this is correct. Minus negative 1 to the third, 3. So this is going to be negative 1. Oh, I see. I have a mistake here. Negative 1. So double negative. Wait. Negative 1 to the third is a negative 1. So negative 1 over 3. And then we have a negative. And then we have a negative. But I combined this already plus. So this one just negative. I think I keep getting negative 1 over 3. Where's my mistake? Did you notice? So I think I have a negative 1 over 3 minus negative 1 to the third over 3. So that's negative 1. Double negative change to positive. So I got negative 2 over 3. Oh, I see. Where's my mistake here? I do have, okay. 1 second. So we have a negative 54. So I have a negative 54. Yeah, I'm fine. So double negative, change to positive 36. So I got 108 positive number. So I will double check, but I think this number is correct. So that's the area of that function in three-dimensional space. Anyway, so the second way, we have two different formula. One is just using the parametric equation, or the second one, you're going to use both parametric and polar coordinate system. So check this out. So that's it, 6.2. I'm not going to talk too much. So one idea is later, this idea, you can also expand it to the three variable of the function. So it's the same thing. You can use either parametric equation or parametric plus the polar coordinate system equation. So this is a three variable case. It's the same formula. But I'm not going to do here. So you can think about and expand your knowledge. So two variables should be enough. So that's it, 6.2 so far.